Are we ready to go?
Yes.
Yes. So I'll start, I guess. Yeah, so this is a last minute talk because we had a slot. I decided to do some presentations on discrete event simulation in Python. So a bit of background, this is actually something I worked with for quantum networks in our simulator. And since I had a bit of fun with Python doing it, I wanted to sort of do a return on experience and share what I found out about doing discrete event simulation in Python. So I will explain what discrete event simulation is as well. That's a bonus. I will be using all sorts of Python gimmicks. I'll normally explain them as I go, but don't hesitate to ask if there's something that needs more explanation. And then I'll go down a rabbit hole with generator functions because there's fun stuff we can do there. So real quick, discrete event simulation, what is this? It's a form of simulation where events happen at atomic moments in time. So every function you're going to call, everything you're going to do at a specific moment in time. And then you're going to say, next event happens whenever. And so you're going to be scheduling events for later and then executing events in order. And of course, events can schedule later events. This is really convenient for distributed algorithms where a bunch of different events can occur, schedule themselves, and you don't have to keep track of how long do I have to wait until the next event and things like that. So the basic implementation for discrete event simulation uses a priority queue. A priority queue is a data structure. It's a heap. So basically, you can put things in. And when you pop an item from a priority queue, you always get the smallest item for whatever comparison function you have in there. So generally, the priority queues in Python, there are two of them. I use the easier one, which is from queue import priority queue. There is another one, which is a tiny bit harder to use because it's not a class per se, but which is probably more convenient for simulation because priority queue is thread safe, but you rarely do one simulation on multiple threads or you're going to have concurrence issues. Normally, you need events to happen one after the other and the order matters. So priority queue is great if you have multiple threads, and heap queue, I think the other one is called, is probably better for simulation purposes, but it's also a little more complex to use. So we're going to create a priority queue. If I can find my mouse. And we're going to create a time, which is where I'm at in time at any given moment throughout the simulation. And the most important thing to look at is what happens when we want to schedule a future event. We give a when and a what. When is the time at which the event should execute. The what is what function I should run. And we basically put in the priority queue a tuple, because as I said, the order matters. So you're going to put the when as the first parameter. And we're going to use a counter, which increases every time we schedule something, to just break equalities. Otherwise, it's going to try to compare the what, which is a function, and it's going to fail. So this is just us putting stuff in a priority queue in a way that the when is going to decide which item is on top. And then when we run our simulation, while the queue is not empty, we're going to get the top item with get, and we're going to look at the time and the function, set our time global variable to time, to the time, and then call the function here and here. If we put a stop parameter on our run, we can also stop once time reaches that horizon, simulation horizon, where we decide to stop the simulation. And this works. So we're going to run it. And the simplest example is I'm going to schedule 4 events. I did not put them in order. So if you look at the time on the screen, they're in random order. But if I run this, they will be called in the right order corresponding to time. There. Since we're passing functions to a function, I'll be using a lot of lambda functions throughout because that's the convenient way of using this. The other option generally is partial. from functools, the partial function, which allows you to do the same thing. I find lambdas more convenient.
Sorry, what was the other alternative to lambda?
Partial. So from functools, import partial. Partial allows you to prepare a function with arguments to be called later, with part of its arguments. So what you could do is, I'll do it here. Functool. What partial does is it prepares, so if I want to like add something at time, say 2, and I could write partial print. No, this is not going to work actually here. This time is going to be taken the wrong time. Here, sorry for people on the bridge. Time is going to be used at the moment when the function is called. Here, it's going to be used at the moment where I'm preparing it, so it won't work. But this will, in some cases, be useful to sort of provide arguments ahead of time to a function you want to call later. That's what partial is used for. Okay, so this is great, but we prepared all the events before running the simulation. One of the nice things with discrete event simulations is when you start scheduling events as you simulate. The most common example is basically a loop, an event which will re-trigger itself further down the line. So for example, I want to print the time, and then I want to schedule for in one time step. Sorry, I shouldn't say time step because we can have real valued time, but in one time unit, call myself again. I schedule it at time 0, and here it's going to do an infinite loop. So I make sure I put a stop and stop the simulation at time 4. And I'm just calling print over and over and over, rescheduling it to be called one time later. So this is a bit cumbersome. And one of the nice things you can do off the bat is use decorators. So look, so we're going to decorate. We're going to use decorators to improve this. Just quick recap on decorators. They are functions that improve other functions, replace them. So here, for example, if I have a double function, which does something very natural, and I want to enhance it, I can use a decorator. And a decorator is just a function which will take a function as a parameter and return a wrapper function to replace it. So the syntax here with the at is equivalent to doing double equals log of double, replacing the function. And I have to provide a new function to replace, so a wrapper function. Generally, what the wrapper function does is it doesn't know anything about the function, so it provides arbitrary arguments, and then it'll call the function with those arguments and return the result, and then it'll add other stuff around here. So for example, log here will run the same function it's logging, but before calling it, say I'm going to run it, and after calling it, print the result.
Yeah. The arrobas wraps decorator ensures that the docstring and stuff like that is the same.
It makes the wrapper function look more like the function. An example I can actually, here, I'll get to it in a second. Here, for example, I log that I'm running the function before I run it, and then I log the result. I get the function name through func.name. What's interesting here is if I do print double dot name, double is called double. If I don't have the wraps, double is going to be called wrapper because that's the name of the function I'm calling. So yeah, wraps is a nice utility when you're doing decorators, which allows you to really say this decorator will look from the outside like the function it's wrapping. As I said, I have a bunch of Python gimmicks in there. Don't hesitate to call me out when I forget to mention one.
So
yeah,
basically, you could do the same by defining a function.
It is a function.
Yeah. So but I mean, instead of using wrap. So the advantage of using wrap is when you don't know everything about.
I don't know anything about the function.
Exactly.
Wraps is going to look at the function, look at its docstring, its name, and things like that, and copy them on wrapper.
Right. Even the arguments can be whatever, while
Oh, here, so there's two things. There's wraps, which is going to change the wrapper function to look like func, and the wrapper function itself, which is what I'm going to be returning, which can be anything. I'll have examples where the wrapper function doesn't have the same return value as the function it's wrapping. You can do that. Linters tend to have trouble with that because they don't know what your function is supposed to return after a while. So in terms of meta programming, it can be a bit more tough. But there are use cases. I have one coming up right after, actually. I want to do, so again, look at the usage first. I want to have a decorator which runs a function a certain number of times when I call it. So I define print hello, which is just going to do a hello world or a hello Alice. But I've wrapped it with run x times. So it's going to call it, when I call it once, it's going to call it 3 times. So here, what's interesting is I have a parameter. So what I need is I need run x times to be a function which takes a parameter and which returns a decorator, which will then be applied to print hello. So run x time takes a parameter, defines a decorator which is going to return, and that decorator takes the function and wraps it, and just loops over the function a number of times.
So just to be clear, without the wraps decorator, this code will still work.
Yeah.
But the name would be decorator, basically.
The name would be wrapper.
The name, yeah, sorry.
Yeah, there's a bunch of functions. But yeah, there's doc strings. Like if I mouse over, I don't know if I have it in. No, I don't have it here. If you do mouse overs in some certain editors, it'll show you the doc string.
Yeah.
If it wants to get that right, it needs to know what the right doc string to look at is, and that's what wraps does. It's really a neat utility you should be using. It doesn't change unless you're doing meta programming and looking at in your program at the name of the function. It shouldn't change the code. It also helps when you've got errors because the logs will give you the right function name rather than wrapper.
Yeah. What do you need the intermediate decorator function?
Run x times 3. I call it 1. So this is going to be called on 3. Return a decorator, which is then going to be used on this. Is that clear? The decorator is run x times as 3. So run x times takes a parameter and returns a decorator.
Isn't it possible when you do a decorator to add parameters after func? You do something like def decorator func, comma x. Because there are.
No, I don't think so.
In the wild, there are decorators that have parameters. So.
Yeah. Well, here I have a decorator with parameter.
Yeah, sure.
But in the implementation, as far as I know, the implementation is always a function that returns a decorator. You can have fun trying to do a function that takes or doesn't take parameters by checking if the first parameter is a function or a parameter and behaving differently. There's a ton of things that do that. But if you want parameters for your decorator, you need that extra outside function.
What I think it does is decouple actually the function definition with the parameters. So basically what you want to do, you can add it in run x time. So in the x, you can add as many.
Yeah, sure. Yeah, sure. I understood it as that, which is one.
I don't think there's an overload. No, no. Decorators are syntactic sugar.
Yes.
So you're defining syntactic sugar.
Yeah.
Generally,
More sugar is
the only syntactic sugar up there is the wraps, which does a lot of work for you. That being said, we can now come back to our simulation and our loop example where we were reiterating over a print statement, which was rescheduling itself. And we can have something where I want to say, look, for my simulation, I want you to loop print time loop every 1 instance. So this is going to do the same thing as in the previous example. I'm going to this call here schedules print time loop and reschedules it when it's called every time. And we do that by defining a loop iterator. I'll get to the parameters in a second. In terms of functionality, it does 2 things. A wrapper which schedules itself to be called again later. So this is what we had in the initial example above. I'll come back to it. Sorry. Where was I? Here, when we were doing the print time loop, we were doing our stuff and then rescheduling. And here, I'm going to do that again. Do what my function was meant to do and reschedule. And I'm also going to schedule my function initially once to start. All this in loop. So I have a default start parameter, which if I want to delay the first occurrence and not be at time 0, I can do that. And then the interval at which I want to loop. Syntactic sugar. There was a question?
It looks more complicated than the code that you wrote above.
The decorator is more complicated, but once you've written that once, this is easier. And if you use that, if you have 50 events that are looping all over the place, this is a lot easier to use and readable. So yeah, when you're doing this and building your simulator, generally you've got building the simulator and using it, and you want to build your simulator better so that usage is simpler. So this is providing ourselves with syntactic sugar to ease simulation. Think about it as I would go an extra mile when building a module to make it easier to use.
Yeah.
But I agree, this is, when you're not used to decorators, this appears like a lot, but afterwards usage is really simple. Okay, why? Because if I look at how I scheduled functions initially, the what function is always called without parameters. So in my simulation, if I want to provide a function with parameters, I'm going to use the lambdas here and pass the parameters here. But the function itself that's scheduled is a no parameter function. So I use that, yeah, I didn't put any parameters in the loop specifically. In other wrappers, I had the parameters. In loop, I know I'm going to loop on functions which I'm never going to call with parameters, so I removed them. Clear enough? Syntactic sugar, this just says every parameter afterwards has to be called by name. This is something I do a lot with. I do a lot when I don't want, because if I don't do that and I do loop and 2 parameters that are just numbers, you never know what those numbers mean. So I tend to sometimes force naming the parameters when I call it here. I couldn't call it like this. I have to do this. It also allows me to have a default parameter before a non-default parameter, which is neat. I said I was going to put a lot of syntactic sugar throughout this presentation because it's a good way of seeing them in practice.
Anyway, since they are keywords parameters, the order really don't matter.
Yeah, you can actually put parameters before the start, in which case you can call them without the keywords, and you can have a mix where you have non-keywords and keywords. You can even force some parameters to not be callable by keywords with a slash.
What's the utility of that?
I don't know. Honestly, unless, no. If you have, okay, if you have args like this, everything after args has to be keyword. And args itself, you can't name the arguments inside. But I don't know of any use. No, the only use case I know is if you're designing a module and you're saying, these parameters, I may later change their name. So never call them by name.
Or for backward compatibility.
Things like that, yeah.
Because you can inherit this method in a inherited class,
Yeah.
and then the previous loop definition may have some internals where they were calling without names, and so with this you just extend the functionality without necessarily changing all the parents definition.
Generally, it's about creating modules and being future safe. About saying, I may change this later, so don't call it with parameters. You want to guarantee that the function signature is always the same. So if I don't know if I'm going to move my keyword parameters around, I want you to necessarily call them by name. And if I don't know if I'm going to change the name of my parameters, then I don't call them by name. There are use cases. I'm a very keyword centric person where I like.
Otherwise you risk to have a mess later.
Yeah.
You will not understand what's happening.
I've had cases where for a vector x, y, z, I force people to say x, y, and z, which is the extreme.
So for your just to
Yeah.
for your use cases, you could have just used the asterisk arc, right?
Yeah, but then I would have to separate This is actually the same thing as calling this, except I'm not using it. I like to think of it like this.
Okay.
It's saying we're not using args, and you can actually skip the underscore, is what it says. More, because we're doing simulation, a more complex example, almost, is a random walk on 0 to 10.
Just a small remark between replacing star by star args.
Yeah.
If somebody does a typo like start instead of start, putting equal args is not as good because it will go into the args and there will be a silent bug which is that the start time will not be the one intended.
Yeah, if
So
they
it's better to do like
no, because if they name the parameter explicitly, it can't go into args. It has to go into keywords,
yes.
which I didn't put. However,
True.
if I put args
Yeah.
and they provide
Just a number.
no keyword, then it'll change the behavior.
Yeah, but there can be a silent bug.
Yeah. So simple random walk. I have a position, which is going to be something that involved between 0 and 10. I have bins where I'm going to count how often I was in each position, and then I'm going to loop. And each time step, I select a random integer 0 or 1 and move either left or right. Minimum 0, maximum 10. And then I log the bin I was in. And if I run that simulation, I have an easy simulation running where I know how often in those 1,000 iterations I was in each position. So this you could do very easily without all the stuff I did this far. What becomes interesting is if I want to say, okay, but instead of measuring the position every time, I want to measure every 10 steps. And I also want to have an offset where I start later because I want it to sort of mix at the beginning. And so here the bins are going to be less packed, of course. But you can start to see, I don't have to worry how often I need to call one or the other. I don't have to say, oh, should I be measuring now or not? I've just started both things separately and they'll happen on their own. And the interference between the two disappears, which is convenient, especially when you start having 20 different things happening at once. You don't want to have to think about which one is the next based on your knowledge of all of them. You just want to put them all in the priority queue and not worry. This is really the strong spot for discrete event simulation. Last example before we start having fun, ping pong example. So I have Alice and Bob, which are two functions. Alice calls Bob, Bob calls Alice. One of them prints ping, the other one prints pong. And of course, there's a delay of 1 between each call. So this is really events scheduling other events and back and forth. If you're doing network simulation, this happens all the time. A network query is me telling somebody else to activate a function after a given time. There. And now I want to give a more complex example and justify the use of generators, is that's what I want to get at. So I'm going to give an example, which is downloading chunks in a peer-to-peer network. Suppose you have n individuals. Each of them has one chunk from an n chunk file. Every chunk is present once in the system. And I'm going to start, each client is going to start randomly looking for one of the chunks they're missing, chosen at random, and start asking peers at random, do you have that chunk? Once they find it, they have it, so they can now answer, I have it, if somebody asks them, and they start looking for another chunk at random. They do it chunk by chunk. The order of the chunks is random. The order of the peers they ask is random. If I were to do that in the simulation, oh boy, it's going to fit. So internally, every client has an index and a list of missing chunks. When you start, it's every chunk other than the one you start with. So we give them their index and their initial chunk. And they're going to keep internally, what chunk am I looking for right now? And who are the peers I haven't asked for that chunk? So when we decide to download a missing chunk, first thing we're going to do is, do I have one I'm looking for? If not, I'm going to select one at random from the missing chunks. So choice is just from random. You've got a random choice function which chooses at random uniformly. And not asked, I'm going to initiate it to every peer, so everybody except myself. And then I'm going to choose a random peer from those I haven't asked yet. So this is initially if I haven't got a chunk I'm working on, and then whether I had a chunk I was working on or not, select a peer I haven't asked, and then schedule a call to that peer's onQuery method, which is the method they're going to execute when they receive a query. The onQuery method is very simple, do I have a chunk? I'm asked. If I don't have it, I'm going to reply with none. If I do have it, I'm going to reply with the chunk number. For fun, I add a random time, so this is the time for the answer to go back. If I am sending the chunk back, I'm going to add a second random time to say it's longer because I have to send the chunk. This is me doing the simple route to just change things around. And now a client has to do, when we're receiving a reply, we have to implement the onReply, where if the chunk is not none, then I can remove it from the missing chunks. I've acquired it. I reset my query because now I'm not asking for that chunk anymore. And I do some print stuff just to say things are going well. If the chunk was none, I have to remove the peer from the peers. I have to say this guy didn't have it, moving on to somebody else. And then I schedule myself again. Note there's a return here. So if I got the last chunk, I won't be scheduling myself again. The order is probably not the best when I wrote this rather quickly. Does this whole process make sense? Do you agree that it's kind of hard to read and hard to follow where I'm at? So it works. I can build my initial chunks, shuffle them. Again, this is from the random library. Build my clients with variety in their chunks, and then schedule their initial download, run it, and print the time at the end. So I'm going to see all the logging, and at the end, I have how long it took for the last person to get the last chunk. This works, but it's hard to read. And what we'd like is something more like this. Warning, it doesn't work. Where looking just at the download missing chunks, I'm going to copy the list of missing chunks and shuffle it. This is the order I'm going to be looking for the chunks in. And for each chunk, create the list of peers and shuffle it. For each peer, query for the chunk, look at the success, and if the success is not enough, remove it from my missing chunks. So here what I did is I basically combined download missing chunk and onReply in one function. And because I did that, the function becomes a lot easier to read. The whole algorithm is a lot clearer. Of course, schedule doesn't return anything. And here, the problem is, while I'm waiting for the response, other functions have to be called. So here we have an issue. That doesn't work. I'm getting to it. Same thing for onQuery. We do have to be able to reply. The idea is to reply after some time. The reply, again, after some time doesn't mean anything in this context. We want to say, send that reply, but pause first and call other functions while you do that. So how do we do this? My first try at this was using await, saying success equals await schedule using the await keyword from async.io, because await pauses the execution of function and allows other functions to happen. The problem is async.io is async await is really tied into the async.io module, which is really tied into the input-output operations, and you necessarily have system calls if you use await, which will slow down your simulation. It was a bit of a pain.
Is it using threads under cover?
No, it uses the same event loop we had prior, except it has its own implementation of the event loop, which is built in and which is hard to use, which is why I steered away from it. But we have another magical keyword instead of await, which is yield. So here, instead of await, I'm going to use yield. Say, here, I'm going to call a schedule, and I'm going to yield. I'll come to what that means in a moment. And same thing on query. When I receive a query, I'm going to wait. This is me processing. Well, this is the network And either I'm going to return none after the wait, or I'm going to wait again if I have to add the download time before returning the chunk. This code can work. And by the end of this presentation, hopefully, if I have time, it will work. So we're going to use generators, which is what the yield keyword does, to actually make this simulation possible. We're going to change our simulators so that we can write code like this for simulations, code which is a lot easier to read and write. And when you start doing network simulation where you have calls where you're requiring something, getting the reply, doing another request, doing the reply, it avoids having 10 functions and not knowing which one is called when. You can actually have a simple code. Yeah.
The last time I looked into the code of NS2 or Omelette, it's more the first style of things, right?
Yeah.
They don't use these.
I haven't looked at that yet recently,
Sure they,
but so here yeah, there's no yield. I'm not aware of yield in C++.
Well, there is, because underline, the thread can choose to yield their CPU, but
you have to multi-thread it. Yeah, you basically have to spawn a thread for each concurrent function that is being called.
They don't do that.
Here, it's mono-threaded.
Yeah.
My JavaScript background is probably showing at some point because this is what JavaScript does with await async. It has a loop, single-threaded loop, where functions are paused and resumed later. A function that pauses and gives back the hand to whoever's calling it exists in Python and is called a generator, and it's what the yield keyword does. So, quick recap on generators, because this is where it gets tricky. A generator, the most common use case for generators is creating iterators, meaning something I can iterate on. Here, basic usage. So I'm going to create a first generator on top, which is basically going to do what range does. If you write range n, it returns values increasing. So if I want to do that, I just have a generator where I start with I equals 1, and while I is less than n, I yield the value of I and increment it afterwards. And if I do that, I've created a generator, and here the loop is going to ask the generator to give it a value every time until it finishes, and that's what I is going to be. So this is really the same. This is basically how range works. Note that at no moment in time do I have an array. There's no, you can iterate over an array, but you can also have iterators, which are going to spawn the value over time. And a generator used like this is basically an iterator. If we look at what's happening under the hood, this loop, this for I in generator loop, is actually doing a while true, asking for the next value. So next is a built-in function Python, asking for the next value from the generator and printing it. And at some point, the generator is going to raise the stop iteration exception to say, I'm finished. This is exactly the same loop. This is how it's built into generators. And then we can take it one step further, because if you look back to what I did here and what I was proposing, yield, so returns a value every time I call next, but it also expects the value to be sent in. So what's happening is I'm returning a value when I do yield, and when I resume the execution of this function, I expect to resume with an input value that is provided. And you can do this in generators by replacing the next g with g.send a value. This will resume the execution of the function while providing that value as a return from the yield. So, small fun example, the more or less game where you give a secret value and you have to guess, and I tell you if it's more or less. We define the game with a secret, so say 6, and we're going to ask for the person calling the generator to guess a value, and every time they guess a value, we're going to return a string which is it's less than that or more than that, and if they find the right value, we're going to return raise stop iteration. So I have to call send or next once with no value at first. Why is this? Because here I've created the generator. I haven't started iterating, so I haven't actually started running any code. If we're looking at where we're at in the function, we're here. So I have to get to the first yield before I can provide a value. So the first execution before this first yield, if I had, for example, a print here, that print will only be called the first time I start executing the generator. So after the first next or the first send. And only then will I be able to start inputting values. Is that clear? So the first send has to be none because there's no yield here there's no way to retrieve the value, and could yield something other than none, but here I'm yielding them. And then I'm going to send and print whatever game is returning until game stops. So when I guess 6, here j.send is going to raise stop iteration. I won't print anything. And I'm going to retrieve the return value, secret, and print it. So this more than 5 is the result of print jsend 5, jsend 10, jsend 6. Here, I'm not printing anything because I raised the exception. I am retrieving the return value and printing that. What's important?
Rémi,
Wait.
can you hear me?
Yeah.
I was wondering if you remove line 2 and 8, wouldn't it work?
How do you get the first guess in line 3?
Could you, for example, write, okay, replace line 2 by guess equal none and remove line 8, for example?
I don't think it works. I'm pretty sure you can never pass a parameter. Well, you can. The first parameter is always ignored. Meaning, take again the example where you had print here. When is that print called? That print has to be called at some point when you're. It will not be called line 8. It will be called line 9. There's a setup where you have to do an initial call to start running the generator before the first yield, and you have no way of retrieving the value that is sent on the first send. If you find a way around this, I'm curious, but looking into it, I
was wondering what would happen. Okay, no, you require the while.
remove this one, but
yeah, let's try.
Sorry, because guess equals none.
Here, yeah, guess equal none. You remove line 9. Okay, can send.
You cannot send a non value to just start a generator, which basically.
Okay. Okay. Got it. Thank you.
And then to answer, yeah, I'm doing it.
Just do the same test as before.
Oh.
Yeah, like this, and picking next G instead of.
Yeah, that's basically what we were saying. Creating the generator does not start executing it. Yeah, and the problem is if you do next, but you don't have that initial yield, you're sending a none to the first. Sorry, when you walk into while here, you know that at this point guess is none, right?
Yes.
You do need to get the first value at some point.
But I think what you can do is just yield on game secret and then put guess equals none, or no, actually guess equals none and then yield. That I think will work.
Yeah, but it's going to do the same thing.
It's going to do the same thing, but
you still need that send none here.
Yes.
You're basically doing this first.
Yeah, and then you don't need to do guess equals yield none. You just yield. Just write yield, and then you release the control to this function, and then you return it.
If I just you want to do this?
Yeah.
No, because after the second send, guess here is none, and this is going to fail again. I'm pretty confident that there's no way to work around this.
Okay.
Are we okay with funky generators? The interesting thing here is I have really a way of doing a back and forth with a function, passing data one way and the other. Yield gives me a data when I do j.send. Sorry, when I do j.send, I input a data. It's going to run till the next yield and return a new data to me. And this is synchronous. There's no pause in there. And then later, I can resume execution of that function by redoing a send. And this is how we're going to get this thing to work properly. We just need the event loop and the functions that are calling our functions, the loop that is calling our function. We need to make sure that it's able to handle these yielded returns in an interesting way.
Another way to phrase this is to say what is between dev game and yield none is what you obtain when you create the generator. And then, so you pose your generator on the yield none. And then whenever you call next, it will process the function until reaching the next yield. And so you repeat this until you raise a stop iteration exception, which stops the iterator. But indeed, you require something to delimit what is between the construction of the generator and the first iteration. And that's why you require this yield none. This is what I didn't get earlier.
When you do line 7, create the game, you create the generator, you do not start running it. This is
right. Exactly.
Really important. And you need sort of an initial call to run it.
But actually, it gives you the opportunity to do something between line 7 and 8. Because if you write some code between line 1 and 2, it will be executed when you call the constructor, so line 7.
No, when you write something between line 1 and 2, it's called when you run line 8.
Seriously?
Yeah, if I do.
Yes, try please.
If I do this and this.
Yes, go ahead.
This is called first. We haven't stepped into game yet.
Okay. Interesting.
Long code.
Yeah.
You see that just that on the screen, and then if this is like the bottom, you cannot understand what's going on. So
your code is going to execute. If you look at a long function, the code is going to execute. When you see a yield, yeah, you know, okay, here it's pausing and waiting for another input from whoever's calling it. What's important is you do not call a function and a generator the same way. I agree with that. If you see a function and you don't know it's a generator, you're going to mess up.
Better to add like a comment. This is a generator.
Yeah. In my things I didn't do but said we should do this if you were going to do like a proper module, something that makes sure that every function is a generator. What you can do is a decorator, which looks at the function and says, if it's a generator, okay. If it's not a generator, transform it into a generator. That's easy to do. And then from there, you can sort of expect the function to always be a generator. And I'll show you how to build a generator when you don't have one, which is fun.
So the sandwich.
Yeah.
It's the only function you can call the generator, or
No. I don't know the API for generator off the top of my head. Next, when you do next of j, it actually internally calls a function called next, __ next, I think, which you have to implement if you do. So there's two things. There's generator function. It's kind of all a mess. But there's a bunch of functions on there. But the basic usage is, yeah, you've got a function to walk into there and get the result.
Yeah, it's repeated. If you don't know there is a yield in the function.
If you don't know there's a yield here, you may miss it. Yeah. So generator functions are not used like functions, despite the syntax. This is why async await, when you use async await, you've got this async here. Sort of say, careful, this is not something you should use as a function. Generators don't have that. You can also build generators as classes, implementing the next, etc. But generator functions, this syntax, is very useful to write them because it's very natural to write. It's what we want to do when we do simulation. But to get that under the hood, you have to do some tricky work.
So
Rémi, maybe you said it, but am I true if I have the mental picture that each time, in fact, the generator pauses, it's after doing the right part on the equal of the yield,
Yeah.
it's at
Yeah.
the equal point. So it executes the right part, which is
Yield.
the yield. Pausing at the equal doesn't do the assignation of the
Yeah.
left part. And when you resume the function, actually it does the left part of the equal
Yeah.
in some sense.
Yield returns what's on its right, and when you resume, whatever you provide with send is assigned to the left.
The left
It's
part.
a value of the
It's
yield.
very counterintuitive.
You can have, you can also, okay, I'll do it here. You can also have functions like where I'm calling J, yielding its value, and when I'm called back and I get the value that's with send, passing that to F.
Yeah.
It doesn't have to be an assignation.
Yeah.
Force of habit. When you get used to it, it's easy to read. When you're not used to it, it's a bit of a mess. I agree.
But in that case, with your example of F of a yield of G or something like that,
Yeah.
if you use send, what will happen? Because I understand the
F will be called.
the case of an assignation, but
F will be called with the value you provided to send.
That's really counterintuitive.
One way to think about it is, yeah, it's weird. I like to think about it as yielding is asking the caller to provide the next question. Yeah, it's a question to the caller, a yield.
It's a question and you're waiting for the answer.
Yeah, you'll see when I use it in the simulation, it doesn't become clear.
So with this mental picture of you're sending you're asking and you're waiting for the answer,
it's the colleague calling the caller. So back to our simulation and building the simulator to use generators to allow for the syntax for the client above. First thing we need to do is think about what yield schedule does. When you come back up here, sorry if I'm moving around all the time, here, yield schedule is saying, next time, call me. So it's telling the caller, schedule this, and when you get the result, call me again with the result, right? So what schedule returns, what's going to be sent to the caller, is what I call a pending response. It's something that will be a response label later, call me when you get the response. And what a pending response looks like, one way to implement it would be, caller, you get to send a callback when that response is ready. And then when what's in the schedule terminates and has a value, it will call the resolve function, which will basically call the callback set by the caller. Basically, schedule, what it does is say, I have an object, you can listen to it with onResolved, and when I'm finished, I will call resolve and call whatever you provided. I will tell you when I have the result. A pending response is, I will tell you when I have the result. And you can register a callback for that moment. Is that clear? That's the first step. Now we need to look at our generators, and we need to handle them properly. Generators do two things, right? Yielding, which says, oh, I'm going to give you a pending response. You need to call me back when you get the response. And they're also, when they return, providing a response to whoever called them. So they are a generator. There is a pending response in there somewhere. And the handler for a generator, something that's going to encompass the generator and manage it, will be a pending response. When I schedule a generator, I'm going to create a generator handler, which will be a pending response. That generator may call its own yield functions internally. We have recursion, but sooner or later it will return. And when it returns, I will get back to whoever scheduled that generator with the response.
Is it possible to create deadlocks with that? If I do a mess, maybe not.
Probably. I haven't tried to. If you do things naturally, generally not. Yeah. But no, generally you avoid actually doing the, I'll get to it in at the end. You want to avoid calling recursively your resolve functions, your callbacks. What you do is when you're ready to provide a value to a callback, you schedule it for now, as in put it on top of the queue. And that way you're always in a single function, but instead of creating a call stack, you're creating a call queue and you're constantly putting it in that call queue. And that way you sort of avoid deadlocks, unless you've got something which is recalling itself. So our generator handler, it's going to take a generator. Great, that's easy. It is a pending response. So at some point it has to resolve. This is when the generator terminates and gives a return value. It will resolve saying, I've got the final value. What it needs to do on top of that is handle the back and forth with the generator. So I call this wake. The wake function wakes up the generator, which was paused due to a yield, and executes the next portion until the next yield. So when I wake a generator handler, when I wake up the handler, what I do is I send whatever argument I had to wake it up with. This response here is going to be a pending response provided by the next yield in the generator. And what I'm going to say is, oh, that pending response, whenever it's resolved, I'm going to wake it up again. I'm going to send the argument for the pending response back into wake. This is the loop where the handler says, every time you give me a pending response, I will wait for that response. And when it gets here, I'll call you again as a return value for the yield. And so we've got this handler, which is doing the back and forth with a generator. I need to execute these cells or else everything's going to crash. Now, when we schedule a generator, I now have to do two things. I now have to encompass the generator I'm scheduling with a generator handler. Great. And if it's a generator function, I have to initialize it by calling it with nothing. And then I have to put it in the queue. And what I'm going to put in the queue initially is the first wake of that. Last thing, I want to return a handler. Return the handler. Why? Because when I'm scheduling, I return the promise, the pending request. Yeah, promise is the JavaScript term. Sorry. For a long time, it was called promise in my code. Sorry. So I'm returning the pending request so that anybody who scheduled something can listen on the response. And we're almost done. If you remember, there's one last thing I had in my client, which is here I was saying, I'm going to wait a random time. So wait is going to schedule something. And then when it comes back to me, there's no value. What it's going to schedule, what wait is going to do is it's going to schedule a no-op. But when that no-op returns, I'll resume. Now here's the fun thing. If I schedule a, where am I? If I schedule just a no-op defined by def function does return, that's not a generator. We need a no-op generator, a generator which just returns, but which is Python-wise a generator. So the idiomatic way of creating a generator when there is no yield in your function is to just put a yield after the return. Yeah. So you'll never reach it, but Python knows it's a generator. This is just, it's one of those things where you need a way to tell it's a generator, and this is the easiest way where it'll work. It won't have side effects. And people who see that know what it does if they know what's happening, which is why I put it up there.
Because one thing I will know for sure is that after return,
Yep.
everything you write after doesn't mean anything.
If I comment or not this line, it changes everything.
I know. So it violates what people expect.
I have the same
Global
problem.
language.
I have the same problem with global variables in Python,
Yes.
where same thing. If you start assigning to a global variable and forgot the global keyword, it changes what happens after when you read that variable. There are quirks in Python like that. This is one of them. It's a funny one. I wanted to show it because it's good to know. That's how you do it. And then wait is just going to schedule the no-op after the delay. And once we've got that, so this time I can actually run this test. This is the same code as before with the yield schedule here, the yield weights here. This reset is just because when I was doing this, I never knew what order my queue was in. So this is just to make sure the simulation is running. But again, shuffle my initial chunks, create my clients, schedule the initial missing chunk thing, and run. And it runs. And now I can run code that looks like this with my simulator using a bit of generator magic. And I'm pretty much at the end of my time. I'm just going to go really quick through some things you can do more because you can always do more. Here, I didn't create a module, so I have a bunch of global variables. You would want to encompass them. If you're running simulations in parallel in different threads, and you don't want to use a single module because then it would kind of break your non-single. You need a different queue for each one. The best way for me would be to use a context manager with the with keyword where you define a simulator, prepare it, and then when you move out of the context, you automatically run it on close, and you can analyze the results. This would be a nice way to encapsulate. It's one option, but it allows you to encapsulate your simulation and what's happening in a given spot. And if you have multiple to run in parallel through different threads, if you're only running one, just do a module, put everything in there and hide it. Interesting pending results, join and race. Often in code, you will want to do, for example, I want to do 3 requests, and once they've all 3 answered, do something else. The right way to do that is to have something which says, I'm going to run my 3 requests. I'm going to have 3 pending requests objects, and I just want to join them into a response. And then when that response is resolved, do something with 3 responses. This will be called, do stuff will be called when I have all 3 pending requests which have been resolved. I use the decorator syntax for onResolved. You don't have to, but it's just nice sometimes to have that syntax. What this does is basically response dot onResolved. Yeah. Sometimes it's clearer when you have bigger functions you want to do, you can always use onResolved as a decorator because a decorator is a function. If you have a function which just takes a function as a parameter, you can always use it as a decorator. It gets getting some used to. Again, Python quirks that are fun to use. But it's sometimes easier to write because if you don't use it as a decorator, you have to write a lambda or declare the function and then apply onResolved. And this allows you to have a better of both worlds.
The join is equivalent to having 3 lines sequentially.
Yeah, except you can run the 3 at the same time. If you do yield 1, yield 2, yield 3, yeah, you have to wait for the first one to finish before the second one is called. Here, you can do all 3 calls at once.
But the waiting time is not the real waiting time.
The waiting time is whatever you put in schedule. Schedule has when do I run it. So here, the advantage would be that pending 1, pending 2, pending 3 will be returned by schedules, which I can call at the same time.
Yeah.
And race is the same thing, but you stop when you get the first response. And generally, what's going to happen is all of these are going to be none except 1, which is the one you got the response for. An interesting use of race is timeout. If you want to do a request, but say, if I don't have an answer after so long, I'm just going to stop. That's just a race between whatever your generator was and a wait. Very convenient. As I said, transforming scheduled functions into generators if they're not generators to make sure you're always working with generators. That can be as easy as a decorator or as something you call on your functions when they're passed in, something that the constructor of generator handler can do. You can use isInstance to know if something is a generator or not. And there it's easy. Looking at what happens when you raise an exception and pending response. So you schedule something and that thing raises an exception. What you would generally do is have aside the onResolve function, you have an onReject or onFail function that can be called as well. So you have 2 callbacks, one which is called onReturn and the other one onThrow exception. As I said, avoid call stacks and always put things in the priority queue. It's just a bit of extra code. I didn't want to go through it. There's a lot of stuff you can do. It's a rabbit hole. And if you do it properly, running simulations afterward is really nice because you can actually see your logic, work with it, change your code easily without having to change 3 functions at once. So I went down that rabbit hole once and wanted to share the experience. And I think that's it. Okay, no, not questions, just people talking back and forth.
I have a quick question.
Yeah.
About how would you deal with preemption on yield? Because that's a problem. Typically, for instance, in your simulation,
Yeah.
suppose that you have instead of having nodes that can serve as many requests as they want, they have only chunks unit. And so suppose that you have 1 chunk unit, 3 clients requesting at the same time that chunk unit. Then you yield the 3 clients because you schedule them. And then the server will serve only one of these clients, but then the yield of the other 2 must be preempted because it has consumed its own unit.
So there's a few things in here. There's the on query, which is the response from the server, is kind of stateless and not looking at how many requests I have. You could have something that says, if I've got something running, you could, in the client, store a variable, which is, do I have a response in progress? And if yes, that response is probably going to be a request handler of some sort. A pending response. And you could listen in on that pending response and say, oh, when I'm done serving, I can resume and start serving the next one and have a queue of people I want to serve. There's whatever your logic is for buffering requests, you can implement it here. And there's a lot of ways you can do that. One thing I haven't done, there's 2 techniques generally when you get a bunch of requests and you only want to serve at a given rate. There's something called throttling and something called debouncing. So they are in very different use cases. Throttling is saying I will only respond at most once per time unit, for example. And the way you do that is when you get a response is, do I have something in progress? Yes, then I'll wait. So you would probably raise if you were to do that, you would probably schedule a I'm free event for later, just a wait, but you're not going to wait it. You're going to schedule it and store the response. And when that response happens, free it. So at any time you can look, is there a scheduled wait, which means I'm busy right now? If yes, I'm going to wait on it. And when I'm done, schedule something else. You can have an internal behavior for the server, which is always looping. Like, there's a bunch of ways of doing it.
But in this case, I mean, with these, what I see is that yield basically leaves the control to the agents themselves. What I would do in C, for instance, is that if there is a situation like this, then in your queue itself, you need to check all the events that depend on the event that is generated that will not be served, so that you can remove those events, or you can reschedule them, so you preempt this thing in order to do another activity. The fact is that yield is super nice because you don't need to control the queue yourself.
No.
So you leave the scheduler to
Yeah.
the real scheduler.
No, it's very nice. You say, whenever that's ready, call me again.
What I don't see is that maybe for this particular cases where you have concurrence and you have stateful events that can preempt.
What you would do in that case is queue your request and have a parallel sequence of events, which is constantly depiling the queue and emptying it at a fixed rate.
Yeah.
And possibly when you want to enqueue something, if the queue is too full, you have to reject or something like that. But this is what you would do. You would have 2 concurrent threads of events. And to finish what I was saying, so that's the throttling technique. The debounce technique is something you have more where you want to wait 1 second without any requests to actually execute all previous requests. This is used, for example, when you have auto completion in a lot of software, where it'll wait for you to stop typing for 10 seconds before trying to auto-complete rather than do it at every key. So this is called debouncing. And again, it's another strategy of delaying the moment where you execute a task based on a different condition.